Hello friends, I Professor Thakur from Terna Engineering College Dharashiv welcomes you on my YouTube channel for the subject head Control System Engineering. So friends, as far as our today's session is concerned, so we will try to learn this stability criteria used in this control system engineering, whose name is nothing but the Hurwitz criteria, right? So one basic question arises in our mind ki why we are using such type of criteria. So the answer for that question is nothing but what? Whenever it is required for we people to determine the overall stability of that given control system. So at that time, with the help of this criteria, we can define whether that given system is stable or unstable, right? Now as far as the name is concerned, so basically on behalf of his invention, this criteria was proposed by Mr. Adolf Hurwitz. He was a German mathematician. So on behalf of his invention, the name given to this criteria is nothing but what? Hurwitz criteria. So let us quickly go through how to use this Hurwitz criteria in order to determine the overall stability of that system. So for that purpose, this type of characteristics equation we are having with us. So with the help of this simple example, we will come to know how to adopt the basic strategy belongs to this Hurwitz criteria, right? So as we are very much aware of this thing, as far as this closed loop control system is concerned, so how we are defining the transfer function of that closed loop control system, because transfer function is nothing but what? As we know, it is the ratio of output to the input in terms of S domain, right? So for sake of our understanding, in this way this transfer function is to be declared. As far as its numerator is concerned, so within this numerator a finite number of coefficients we are having, which are nothing but what? B0 into s raised to m plus b1 into s raised to m minus 1. So m number of coefficients we are having within that numerator as well as denominator, right? So whether this is Hurwitz criteria or the second criteria in case of this control system engineering, which is again used to determine the overall stability of this control system, is nothing but the Ruth criteria. In lateral part we will try to learn this Ruth criteria. So whether it is Hurwitz criteria or the Ruth criteria, as far as the closed loop transfer function is concerned, so always we are equating the denominator of this closed loop transfer function with respect to 0. That can be correlated as a characteristics equation. So once we are having the characteristics equation of this given control system, then we can use this basic strategy whose name is nothing but what? This Hurwitz criteria. So if we equate the denominator of this transfer function with equals to 0, so its denominator is nothing but what? A0 times of s raised to n. The first coefficient of this s term is a0 plus a1 times of s raised to n minus 1. So in this descending order like this, n number of terms we used to have is equated to 0. Now as far as this Hurwitz criteria is concerned, so we are having one Hurwitz determinant that we need to declare with the help of this characteristics equation. Once we are having with us this characteristics equation, then we can declare this Hurwitz determinant denoted by this alphabet, call it as H, right? Then after that one question arises in our mind, what will be the size of this determinant, right? So the size of the determinant is to be decided by the highest power of S which is present in this characteristics equation, right? Now as far as this characteristics equation is concerned, so again we are having two basic conditions belongs to this characteristics equation. Then and then only we can mold this characteristics equation in terms of this Hurwitz determinant. So the first condition is nothing but what? All the coefficients belongs to this S term should be arranged in this descending order, starting from s raised to n, s raised to n minus 1, n minus 2, n minus 3 up to n. N number of terms we used to have with us. Then after that, each and every coefficient should carry either positive or negative real value. So these are the two basic conditions which belongs to this characteristics equation in case of this Hurwitz criteria, right? Now as we know, the highest degree of S is how much? Are n, right? So we need to declare the n by n or n cross n Hurwitz matrix for that purpose, right? So as you can see, as far as this Hurwitz matrix is concerned, after that we need to define or we need to declare the coefficients of this Hurwitz matrix, right? So here we need to define the n by n matrix, right, which consists of this n rows and n column, right? Now as far as the first row is concerned of this Hurwitz matrix, so what we need to do, as you can see, as far as these coefficients are concerned, right? So this is the 0th number, this is the first, second, third, up to n number of coefficients we are having with us. So within the first row of this Hurwitz determinant, we need to collect all the coefficients which are present at that odd position, right? Odd position starting from this A1, A3, A5 like this. As far as the second row is concerned, so we need to collect all the even coefficients like A0, A2, A4, A6 like this, right? Then as far as the third row is concerned, within that third row, first of all we need to put 1 0 at this position, and after that we need to follow all the elements belongs to this first row, which are nothing but what, A1, A3, A5 like this, right? The next row will be what, obviously we need to put one more 0 and we need to collect all the coefficients belongs to second row. Within that second row of this Hurwitz determinant, already the coefficients are being declared which are being placed at that even position. So the coefficients are nothing but what, A0, A2, A4, A6 like this, right? So in this way, n cross n Hurwitz matrix we need to declare. Then as far as the stability is concerned, so along with this Hurwitz matrix, again the sub matrices we need to declare. Now how to declare these sub matrices, how to determine the overall stability of this given control system by using this Hurwitz criteria. So for that purpose, let us quickly go through this example which is written on that board, whose characteristics equation is nothing but what, s cube plus 8s square plus 14s plus 24 equals to 0, right? Now first of all, what we need to do, we need to map these characteristics equations in terms of different coefficients. Those are being placed at even and odd position. Once these coefficients are being mapped, then after that we need to declare these coefficients within this Hurwitz matrix denoted by this alphabet called it as h, whose size depends upon the highest degree of s which is present within this characteristics equation or the denominator of this transfer function. So here the highest degree of s is n. So n cross n Hurwitz determinant we need to declare, which consists of n rows and n columns. So let us quickly go through how to declare this Hurwitz determinant in order to determine its stability. If the desired value which is coming out of from this Hurwitz determinant as well as the subdeterminants which we are going to declare, if all values are positive, at that time we can say that the given system is a stable system. Generally, now from this characteristics equation, this characteristics consist of this numerator as well as denominator. So the poles and zeros, these two are the important parameters of this control system in order to define its overall stability. If suppose this is the real and this is the imaginary axis, right? So the basic conditions for this stability means what? At what point that system is being called it as a stable system? When we are giving the bounded output, so that system is responsible to produce the bounded output. Means in absence of that input, the output of that system should equals to 0, right? So all the roots of that given transfer function, roots in the sense poles and zeros, right? If we are equating the numerator as well as denominator with equals to 0, so which will cause the 0th value. This statement will gives us how many number of poles and how many number of zeros we are having with us. If we are equating the numerator with equals to 0, so we are getting how many number of zeros we are having, right? Means that will be the special value of this transfer function which will cause the 0th functioning value. Similarly, when the denominator is being equated with respect to 0, we will come to know how many number of poles we are having with us, right? So the basic condition for the stability all the roots are always lying in the left side of this S domain representation. All the poles are always lying within this left hand side. So this is the basic condition of that stability in case of this control system that we need to utilize with the help of this Hurwitz criteria as well as Hurwitz criteria, right? So with the help of this example, let us quickly go through how to declare the Hurwitz matrix as well as how to determine the overall stability of this given control system, whose characteristics equation is nothing but what? Okay friends, so after going through the basic details of this Hurwitz criteria, let us quickly go through how to adapt all these basic strategies with the help of this very simple characteristics equation of that given control system. So as I told you earlier, control system is nothing but what? It is the ratio of output to the input in terms of S domain. So whenever the denominator of this control system is being equated to 0, this whole term can be called as a characteristics equation. And from this characteristics equation, we can determine the stability or the overall stability of that given control system by means of this Hurwitz criteria, right? So basically there are two conditions. Once these two conditions are being satisfied with respect to this characteristics equation, then definitely we can use this Hurwitz criteria. So these two conditions are very simple. First one is nothing but what? All the elements are arranged in that descending order, like s raised to 3, s raised to 2, s raised to 1, s raised to 0. First condition is satisfied. Second condition says that all the coefficients of this s will be either positive or negative. So here we are having all the positive coefficients of this s. So second condition is being also satisfied. Then already we had discussed the basics of this Hurwitz criteria. Each time we need to declare one Hurwitz determinant whose size based upon the highest degree of s. Here the highest degree of s is 3. So the size of this Hurwitz matrix will be what? It will be 3 cross 3, which consists of 3 rows and 3 columns. But along with this Hurwitz matrix, to decide the overall stability of this given control system, n number of subdeterminants which we need to declare. Now the question arises, how many subdeterminants which we need to declare? Here I will write here d suffix k, that much amount of or the kth number of subdeterminants we need to declare. That depends upon the highest degree of s. Here the highest degree of s, so this k is being iterated for 3 times, 1, 2 and 3. So obviously these 3 subdeterminants which we need to declare, d1, d2 and d3. This d1 consists of 1 row, 1 column, d2 consists of 2 rows, 2 column. This d3 consists of 3 rows, 3 column. Here d3 itself is a Hurwitz determinant, right? So one by one we will try to declare these 3 determinants, and if the value which is coming out of from this each and every determinant is positive, then and then only this system can be called it as a stable system. Otherwise this system can be called it as a unstable system. So this is the basic logic behind this Hurwitz criteria, right? So here initially what we will try to do here initially, first of all we will try to declare the coefficients of this d3, that is nothing but what? Hurwitz determinant, capital H. From this d3 we can declare d2 as well as d1. So it's time to declare the coefficients of this Hurwitz determinant or the third subdeterminant, that can be call it as a d suffix 3 or this capital H, right, whose size exactly equals to 3 cross 3. So d3, that is nothing but what? H, whose size is nothing but what? 3 cross 3. So this is how this determinant will look like, right? Now this determinant should carry 3 rows and 3 columns. So how to decide the coefficients of this Hurwitz determinant or the subdeterminant, that can be called as a d3, so which is very simple. For that purpose we need to assign a finite coefficients to this characteristics equation starting from this a0. This will be a1, a2 and a3. Once these coefficients are being assigned according to the basic definition of this characteristics equation, right? So the elements which are being present at the first row of this Hurwitz determinant, which are nothing but what? The coefficients which are lying at odd position. The coefficients which are lying at odd position means what? The coefficient belongs to a1, a3, a5, a7 like this, right? So presently in this characteristics equation, the coefficient belongs to this a1 is nothing but what? S raised to 2. The coefficient for s raised to 2 is nothing but what? 8. So here we need to write this first element will be 8. The second element or the second odd coefficient which is present at that third position. So at this third position the desired coefficient is nothing but what? 24. Here we don't have this third odd term, that is nothing but what? A5. So A5 equals to 0. This will be A1, A3 and A5. Similarly, the second row is concerned. So we need to collect all the elements which are lying at even position like 0, 2, 4 and 6, right? So the first element will be what? S raised to 3. The coefficient of S raised to 3 is 1. The second even coefficient is nothing but what? A2. The coefficient of this A2 is nothing but what? 14. Now similarly, just similar to that A5, we don't have this third even coefficient, that will be what? A4. So A4 equals to 0. This is how first two rows are being completed of this Hurwitz determinant or the subdeterminant D3 whose size is nothing but what? 3 cross 3. Now as far as the third row is concerned, so always we need to remember that the first element which we need to consider as a 0 and remaining two elements are to be drawn from the first row. As far as the first row is concerned, so the elements of this first rows are nothing but what? 8, 24 and 0. So one position is being already occupied. So the first two elements which we need to carry out here, which are nothing but 8 and 24. So this will be the subdeterminant D3. Then similarly from this subdeterminant D3 we need to declare D2 which consists of 2 rows and 2 columns, right? Subdeterminant number 2. So this D2 is to be decided from this D3. So the elements are nothing but what? 8, 24, then 1 and 14. These 4 elements which we need to consider of this second determinant, which consists of 2 rows and 2 columns. As far as the first subdeterminant is concerned, D1. So here this first element itself is a D1 which consists of 1 row, 1 column. So the total value exhibited by this D1 will be what? This 8, which is nothing but what? Positive. Similarly, we need to solve this 2 by 2 determinant, right? So how this determinant is to be solved? Here I will write. First element is nothing but what? 8. So 14 8s are, I think it is 112. In this is the usual way in that mathematics which we solve. So 14 is 112 minus 24 1 24. So which exactly equals to 112 minus 24. So obviously 88, which is also positive, right? So this 88 is nothing but what? The value exhibited by this second subdeterminant D2. In same manner, now we need to solve this Hurwitz determinant, right, which consists of 3 rows and 3 columns. So how it is to be solved? The way in which we are solving this type of determinant in this mathematics. So first element will be what? 8. When this element is to be considered, this row and this column is being skipped. So the remaining elements are 14, 0, 8 and 24. So we need to do the cross multiplication. So 14 times of 24 minus 0, 8 into 0, 0. Then second element will be what? 24. So this row and this column is being skipped. So the remaining elements are 1, 0, 0, 24. So 24 into 1, 24, then 0. So 24 into 24, I think it is 576. So when we solve this entire term, right? So the value which is coming out of from this term is 2112, I think it is, right? So again, which is positive greater than 0. This is also positive greater than 0. This is also positive greater than 0. All three values which are being exhibited by D3, D2 and D1 are positive. So at that time, definitely we can say that this is the stable system. So this is the basic logic behind this Hurwitz criterion, which says that if the value which are coming out of from that subdeterminants or each and every value exhibited by that subdeterminant is positive, then that system is unstable. Whenever we are encountering through this sign change phenomena, so at that time that system can be called as a unstable system. So this is the basics of this Hurwitz criteria, which is used to determine the overall stability of that system. So along with this Hurwitz criteria, one more criteria we are having with us, whose name is nothing but what? The Ruth criterion, right? Or another name given to this criteria is a Ruth stability criteria. So probably in next session we will try to learn the second stability criteria used by this control system engineering phenomena. So I just hope that you understand all the basics things which we have discussed belongs to this Hurwitz criteria to decide the overall stability of that system. Thank you.